We looked in a previous video at a solution for x to the 5 minus 3n. Well, that should be x to the 5 minus 3x plus 1 equals 0. And we found it. Then what we did, well, we found a solution using the Newton-Raphson method. We identified an interval where a root exists. We found we used a value close to the root, and then the Newton-Raphson method caused our answer to get closer and closer to the true root. So the true root, to see it, we used a graph of the function f of x equals x to the 5 minus 3x plus 1. Alright? Now, let's zoom into the graph. This was the root, as I remember. Alright? And we got really, really close to this root. Now, here, suppose we used some value that's further away from the root and is close to the minimum value. Now remember, at the minimum value, f of x is 0. So you would have an indefinite calculation there, an indefinite answer to your calculation, because you'll be trying to put f of n divided by 0. Well, f prime of n here, based on the main equation, the formula for Newton-Raphson method, you would be saying f of n over 0, which wouldn't work. And what we want to do is use a value close to it. Ideally, we should use a value that is close to the real root, wherever it is. But let's use this value, 0.9. And then we see what happens when we use 0.9 as our first estimate. Alright? So we say our x1 is equal to 0.9. Some persons might say x0, and that's where we start. Alright? If you prefer to use x1, no problem. But I mean, if you prefer to use x0, no problem. You would just start with x0, then you go to x1, x2, and so on. Alright? x1 is the first estimate that we have. Now, x1 plus 1, remember this is xn, n is 1, n plus 1 would be x2 is equal to our x1, 0.9 minus our f of 0.9 would be 0.9 to the 5 minus 3 times 0.9 plus 1 divided by 5 times 0.9 to the 4th minus 3. Let's use our calculator to see what that will give us. Calculator. Alright. Oh no, what's going on? Just jump across like that. Alright. Let's try again. Calculator. Alright, so we have our calculator here. 0.9 to the 5 So 0.9 raised to the power of 5 minus 3 times 0.9 minus 3 times 0.9 plus 1 plus 1. Let's put this in bracket. Alright, divided by 5 times 0.9 to the fourth, open bracket, 5 times 0.9 raised to the power of 4 minus 3, close bracket. But before that, we say 0.9 minus that. 0.9 minus all of this equal, we get 4.855. So we have 4.855. Let's look back at our graph. Now you see the reason why they say the estimate should be close. I mean, your estimate should be close to the real root, or else Newton-Raphson will get out of control. It's giving us a value 4.8 something all the way out here, right? So it had swung out of control because we did not use a value that is close to the actual value. Now, suppose we used 1. If we use 1 to do the calculation, let's see what happens when we use 1. What happened to my calculator? Let's try again. Get the calculator. Alright, in this case it would be 1 minus open bracket 0.9, well, is 1 to the 5th, which is just 1, minus 3 by 1, so it's minus 3, plus 1, plus 1, close bracket, divided by open bracket, 5 times 1 to the 4, which is just 5, minus 3, close bracket, equal. You get 1.5. So when we use 1, we get 1.5 as the answer. So it was 1 minus 1 to the 5th minus 3 by 1 plus 1 over 5 by 1 to the 4th minus 3. Now we got 1.5. Let's look at the graph. Did it take us any closer? We used 1, we went out to 1.5. So this was not very near to the root, and it went all the way out to 1.5. Now, if we use 1.5 as our x3 equal 1.5 minus 1.5 to the 5th minus 3 times 1.5 plus 1 over 5 times 1.5 to the 4th minus 3 equal. Alright, let's get back to our calculator and see what happens. Calculator. So 1.5 minus open bracket 1.5 to the fifth minus 3 by 1.5, so it's 1.5 to the power of 5 minus 3 times 1.5 plus 1.5. Oh, 3 by 1.5 plus, what did we have? Yeah, plus 1. So, oh, calculator went away. Plus 1, close bracket, divided by open bracket. It was 5 times 1.5 to the fourth now. 5 by 1.5 to the 4. 5 times 1.5 raised to the power of 4 minus 3. Minus 3, close bracket, equal 1.316 or 17, 1.317. So our answer here is 1.317. It seemed to be taking us back towards the root, right? Seem to be taking us back towards the root. So when we use 1, it was close enough. But anyway, what we want to do is use 0.4. There is a root somewhere here. Based on the graph, when I zoom in, I estimate that that root is between 0.2 and 0.4. It's a little more than 0.33. But let's use 0.4 and see what happens. So we want to find that other root. Our x1 is 0.4. Let's see where it takes us. X1 equals 0.4. Now our x2 is equal to 0.4 minus 0.4 to the fifth power minus 3 times 0.4 plus 1 divided by 5 by 0.4 to the 4 minus 3. 5 times 0.4 to the 4 minus 3. So let's get our calculator. Let's get a different calculator. So we have 0.4 minus 0.4 minus open bracket 0.4 to the fifth, 0.4 to the power of 5 minus 3 times 0.4 minus 3 times 0.4 plus 1 close bracket over open bracket 5 times 0.4 to the 4, 5 times 0.4 to the power of 4 minus 3 close bracket equal 0.334. So it's 0.334. So you see, we were all the way out here, right here. But when we apply the Newton-Raphson, it got us much closer to the true root, all right, which is quite nice. because it's closer to the roots. Now, of course, I want you to practice doing this until you're very much accustomed to the Newton-Raphson method. Alright? So, that was another example of using the Newton-Raphson method to find the roots of equations. And those include equations where you don't have any straightforward way of solving, like how you can solve quadratic equations. Alright, so that's it for now. I'll see you in the next video.